Hey, math people, we're starting up a really good chapter, functions of several variables. In your journey through Calc 3, so far you've only learned about vectors in 3D space and then space curves. But then really deep down was surfaces, the study of two-dimensional inputs to one-dimensional output, creating a three-dimensional shape. That's the beauty of Calc 3, and in some ways, this is where your journey really begins. So today we're hitting up functions of several variables. We're going to do like a 4-part lecture through this alongside limits, continuity, partial derivatives, and then tangent planes and linear approximations. So you can see here we're going to make some connections to the old, branch to the new, extrapolate in higher dimensions, cover what's called level curves and contour maps, and then see that just kind of to the end. This video is for you, Lena. Make sure you use the timestamps. You pause when you need to, and you be patient with yourself. Okay, let's math. So back in the day, in Algebra 1, you studied domain and range of functions that are curvy things, right? So something like this, in goes an x, out shoots a y, right? Well, just going through the basics, right? Evaluating f of 10 is not a wild idea. You would just plug in 10, right? In goes 10, out shoots 3, right? The square root of 9 is 3. And then we also covered, domain and range in both interval and set builder notation. So I'm going to just show all this right now. 3, 2, 1. Your choice if you want to do it. Here they go. So yeah, this creates a curve on our two-dimensional plane. If we were to cover the domain in, let's say, interval notation first, we would just think of this as from left to right, what is the leftmost value we hit? Well, we can accept a 1 and nothing less, because anything lower than 1 would produce an imaginary number, right? You plug in 0, you get square root of -1. We don't like that here. But then any other number to the right of that is perfectly adequate, totally fine, no issues with at all. We can go forever. So we say 1 is good to go, and we put a bracket with that saying that it's an acceptable input. It'd be parentheses otherwise, to infinity. But more importantly, for this class, we can also write this in what's called set builder notation, which hopefully I can maybe prove to you why we need this more than more than that. So with our single variable input, we can study the domain sort of like graphically on like a number line. So every number from 1 onwards is acceptable to plug in. But consider how that kind of loses its utility right away, because once we start doing inputs of more than just a single variable, how can we describe that in interval notation? We need set builder notation, so that way we can describe both x's inputs and y's inputs in terms of its domain for, say, functions of 2 variables, 2 inputs, and then shooting out a z value instead. So as of right now, we have in goes x and out shoots y. So for our set builder notation, we say all values of x are fine, such that, x must be greater than or equal to 1. And that is exactly what this conveys. All 3 of these things convey the same thing. Whereas if we study range, we're not really concerned with the graphical take on that. We generally just set that aside for domain. And every output is fine or required so long as it's positive, right? So you can't crank out a negative number with real input underneath the radical, right? It's just from 0 and then upward forever. So all these values kind of are good to go. We eventually hit 10, right? We just hit it way down the line. We hit it somewhere, over here-ish, right? At 101. So in terms of the range, that's a single variable output, in which case interval notation is just fine. There's no issues with this at all. However, but let's just, match the cadence of, sticking to set builder, and that's kind of what we're transitioning to. We would just say all the y values where y is greater than or equal to 0. Okay, so passing that baton over and extrapolating this into space, we can now study the very same concepts, just with a new function type, right? A function of now 2 variables, where in goes x, y, and out shoots z. So given f of x, y, where that's going to be equal to the log of 2x plus y, we're going to do some Calc 3 things. So, what does this now produce? We once knew math is just curves on a plane, and now we are gonna, branch that out. We've already kind of seen this sort of extension into space, right? Where we can take something that's just a function of a single variable and cylindricalify it, if that's the word, just kind of extend it into space. But we're doing kind of more than just that now. Rather than it just being a function with respect to x, we now see a function with respect to both x and y. And ignore the, I don't know, ripples down here. This is just Desmos freaking out when it gets really close to an asymptote. Don't look at that. Don't look at that. We're not going to save that image. All right, so let's talk about our inputs first. If we were to plug in 1 and 3, wouldn't be the end of the world. We would just plug in 1 here to get 2, and then plus 3. So 2 plus 3 is, what is that again? 5. Okay, so we're going to just have the log of 5 as an output. And then now let's talk about the domain, both in set builder and that's it, because that's all we can do. We can no longer do this interval notation approach because we now have 2 input variables. So this ain't gonna cut it no more. We want to make it such that we have some sort of ordered pair input, so then x and y will both have its own, well, and maybe in unison they have a restraint in this case. Like there are particular numbers for the log, as you can see, that we don't like. We can't produce values on, the, say, this left side. If we were to bird's eye view it, we can see here that well, okay, here's my inputs variables x and y, and here's my output variable z. Well, how can we utilize that to really pull out a domain from that? Let me show you. 3, 2, 1. So we get what's called a surface now, right? So we're done with curves in the plane, and now we're moving on to surfaces in space. So big jump there. We can say that the log of 5 is the output. In goes 1 and 3 for x and y respectively. So the z output is log 5, whatever that is. And then now this is where it gets a little different, right? So the domain is now with respect to x and y. Sometimes people put it as like an ordered pair inside here, where I'm saying y must be greater than the negative 2 times x. This might be a little much, but if we take on the perspective of a bird flying over the surface, we can see here that the bird's eye view take really just ultimately making it such that the xy plane is really just parallel to our screen here. You can see that this looks like a familiar expression, right? If I were to actually even just copy this, I know that my inputs for the log can't be negative, and they can't be 0 as well. We can't take the log of 0, and we can't be negative. So really, if I play around with just that notion, I really just want to graph this such that, well, I can't put in 0, so I don't want to do like an or equal to. I just strictly want to be greater than 0. You can see here that this is really the same exact shape as this. So considering what your like function algebraic like restraints are going to be, aka we can't plug in negatives and we can't plug in 0, well, we just model that. We just say everything that's greater than 0. And of course you could like move this 2x over. That would do absolutely nothing to the graph. Just make it a negative 2x there. It's the literal same graph. So it doesn't really matter how you write it on the inside. But you can see here that if we take a look at this. I just chose to isolate for the y just out of like paying a homage and respect to the old way, and now kind of branching into the new. So you don't have to do that. It's totally adequate to just write it as that 2x plus y is greater than 0. So coming up with the domain, think about your algebraic restrictions just as you would back in algebra, right? So if we want to just keep rolling with this, come up with the range this time around, we can do interval and set builder because the range is just an output of z. And then also play around with this concept of what would happen if we were to fix y is equal to 2. What would then be the product of that? Well, I'm going to show you right now. 3, 2, 1. That's where you practice if you want to. The range, there's no issues with the log. If we think about the log in 2D, the log in 2D, it can crank out any y value you want. It has an asymptote at an x value of 0, which is the y-axis, but it does go up forever. As hard as that is to see, it just does it ever so slowly, and it goes down forever ever so quickly because of that asymptote at 0. So it goes down forever and it goes up forever. I can show that in 3 space, but man, is that going to look not too great because it has to like load all these like little values here, and that's just a lot more computation than it would have to in 2 space, right? So this is going up forever, just ever so slowly, and it's definitely going down forever, as you can see very quickly. So range is infinite, just all z values, where z exists as a real. All right, so what happens if we were to fix y is equal to 2? Well, you plug in 2 as a constant, meaning that the only input that is a variable is just x, so that just goes back to a curve. It's actually just the curve log of 2x plus 2. It's a function of one variable again, when you decide to fix one as a constant. That should kind of make sense. So if we were to look at this, y is equal to 2, you can see here, extended into space, we can see that the intersection of a surface and a surface creates a curve, right? If I had 2 sheets of paper just kind of intersect one another, you would get that line. Same story here. So what we can do, so yeah, from that bird's eye view, we're really just looking at that, at this like curve along this intersection. What we can choose to do as well, if I were to just make this a z, copy this down, and then restrict this to when y is 2, you can see here that it's just this lone curve on the y is equal to 2 plane, which is a familiar friend that we once knew, loved, and worked with not too long ago. So we're just really switching gears into that higher dimension here. So you can do the same thing by fixing x as well. This notion, this concept will be important once we get into partial derivatives. So obviously you're in a calculus class, we're going to be doing derivatives, duh. It's on its way, just you wait. Okay, so consider the following now. What if we had f of x, y, z? Whoa. And then it's looking like this. Do more Calc 3 things. Just because you're in Calc 3 doesn't mean that, oh, well, Calc 1 and 2 is 2-dimensional, Calc 3 is 3-dimensional. Is there Calc 4 that's 4-dimensional? Not quite. Calc 3 is all things multivariable, so we can keep going into hyperspace. So actually, I'm just going to go on ahead here. I'm going to, we can actually plot this in Desmos 4D if we just head on over. Oh, wait. I can't see in 4 dimensions, duh. Yeah, so we live in 3-dimensional space. 4 dimensions is, some people call it hyperspace, and it's not really something we can do too much visualization of, but that doesn't mean we can't extrapolate on the concepts. So if we were to go ahead and produce or evaluate f of 1, negative 2, 13, we could just plug these in as you'd expect. Domain and range behave as you'd expect, and it would be that same like one-dimensional down element that you would expect. So 3, 2, 1, showing the answers here. So yeah, we create what's called a hypersurface, and evaluating this f of 1, negative 2, 13 should just give you 2. So when we write down that domain, think about how the domain is 3-dimensional. So the domain in this case would be your 3-dimensional surface. So in goes 3 dimensions, out shoots that 4th. And the domain in this case would be a solid, rather than the domain in like... if you remember the y is greater than to negative 2x, just kind of being like a like filled in space. This time around, we can play around with this. The domain would just be when z, so think about how we can't have a negative underneath the radical, just like how we saw in algebra. I can say when z is greater than or equal to x squared plus 2y squared, these would be the domain of inputs. So this is a solid figure. I can kind of zoom out and get this figure forever. All these values are acceptable inputs, and then the output would be a hypersurface that we can't quite visualize, but we can think about it as like some people will utilize like color to come up with outputs here, where like, I don't know, closer to red would be a lower input, and then closer to blue would be like a higher output, and that's one way of visualizing, you know, in 4-dimensional space. But we really can't play much around with this further, since we just can't. It's a restriction of our minds. But you can do quite a bit of interesting things, which we'll do throughout this course. However, this does have utility, right? Just because it's something that we can't visualize doesn't mean it doesn't have practicality. An example could be like a weather model. Perhaps there's some sort of storm, and then your x, y, z, and time variables are important to determine, say, the temperature or pressure in a particular region. Another idea could be like some economic modeling. We could have something like income, education level, region, and time. All of those together could crank out maybe an unemployment rate. Kind of continuing this party a little bit more. Finance, maybe an input could be price, volatility, interest rate, and time, and then maybe you can output some sort of like option value. When it comes down to like AI and data modeling, you could have hundreds, even thousands of dimensions as inputs, and just cranking out one output as some sort of predicted value is common in this landscape. So you don't need to be able to visualize it for it to have utility. All right, so visualization is clearly some key, it's a useful element to mathematics, but it's certainly a crux when it comes to visualizing in space. So for example, literally what we're doing right now, graphing on Desmos 3D, this was not an option for me when I was in college. So this is fairly new technology, at least in this particular graphing tool. Back when I was in college in the 2010s, I would have to like look up applets at like independent universities. There'd just be like some guy, some professors like, you know what, I'll make it my own, and it would just load and crash my device because it'd be some sort of applet. Well, anyway, we have graphing devices today, but there's still some utility in looking at, like, say, a two-dimensional model of something that could be three-dimensional. So, for example, if you are hiking, you may want to know where the steeper slopes are and where more of the chill, sort of steadier slopes could be. So we utilize what's called a collection of level curves to create a contour map, where you can sort of have a two-dimensional flat imagery of something that has much depth to it. Something to kind of study along it is that when your level curves are closer together, that creates like a steeper slope. So for example, maybe each of these level curves represents an increase of I don't know, 10 feet or something like that. So you can see here this would be quite steep if this is a 10 foot, 10 foot, 10 foot, 10 foot, 10 foot, 10 foot jump, whereas something that's a little bit more chill, you have this like very large gap in between these two. So this might be 10 feet high, this might be 20 feet high. This seems like a relaxed slope compared to one that could be virtually like a wall. So obviously we're not looking at mountain ranges. We're going to be looking at something a little bit more manageable, like a paraboloid. So consider the anthill. There it is. We'll start there. Created by just 8 minus x squared minus y squared. See if we can come up with the level curves at 0, 4, and 7. So let's just start with that. I'm going to give you a little bit of time to think about what this may look like. So my hint before you try these out, just to plug in these constants of 0, 4, and 7 respectively for the output here. So for all of f of x, y, to see what that would look like algebraically, and then think to yourself, okay, this is a familiar curve. What is that curve? I'm going to give you 3 seconds. 3, 2, 1. So yeah, x squared plus y squared equaling to a constant value. All right, this equation right here, let's go. We're just looking at some circles, right? And it should make sense that if we were to place this constant output, you know, that's what I'm covering up here, the 8, 4, and 1. You can see that at each, like, this would be to the anthill like a parallel to xy plane cut. You would end up getting like an intersection that is just a circle. Let me demonstrate. So this is my anthill. What we can say here is z is just equal to some k, and we'll just slide that from 0 to 5. Why not? So making that a different color just to make things a little bit more clear, we can see that the intersection of the paraboloid and the plane is always going to be a circle every single time. And then if we wanted to drive that home just a bit further, we can see here that through and through, we're just getting a larger circle as we go lower and a smaller circle all the way up to like 8 as we get higher, because as soon as we get to 8, what would that even look like, right? That would just be our fixed point. It gets smaller, 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 bam, and right at 8, it's nothing because it's just going to be the top of the anthill. There it is. Okay, so we can go ahead and plot this on a two-dimensional plane. So that would just be, well, you tell me. 3, 2, 1. Here it is. Collection of level curves. Okay, let's try that again. 3, 2, 1. All right, there it is. Kind of like a dartboard of sorts, right? So it's just a bunch of circles, right? So if we just have x squared plus y squared is equal to 1, and then we can just do the next 2 level curves here, 4 and then 7. Yeah, well, all right, we can just keep that cadence going just to see that it's just going to be ultimately, at the end of the day, just a bunch of concentric circles. So if we wanted to, for fun, make the circles closer to one another or make them more spread out, we can see that, well, creating bigger slopes, well, we would have a more intense slope creating this effect right here. that steeper slope. So since we would have a more intense slope, then the level curves would be closer to one another. Likewise, if we wanted them more spread out, we would want to create a more chill slope, so something that is not as high. So that is a smaller coefficient for each of these x and y's. We can see that in action right here. So what I've done is I've just played around with the coefficient of x and y. So that way, if I were to make this a more intense slope, it would be harder to climb this mountain for sure, and then a less intense slope, it would be much easier to climb this one for sure. So I can bird's eye view it and turn off the surface, so that way you can see these are fairly spread out for a coefficient that is smaller than 1, and then as I get closer and closer to a larger coefficient, you can see we climb that mountain so much faster, and those are very tight next to one another, hard to distinguish the spacing in between them. And then we also get like a fun shape if we do it that way as well. Whoa. All right, I gotta show that at least once. Okay, just bringing things home here. So match the functions below with their corresponding contour plot. So yeah, what we're gonna do here is just think about these as the intersection of a bunch of planes crossing through at maybe z is equal to 1, z is equal to 2, 3, and then their corresponding graphs as contour maps. So see if you can do the connections, the matching right now. 3, 2, 1. All right, are these your cards? Go ahead and take a look at these in Desmos 3D. That gives us a good visualization of what's happening. So for the first equation, it was y squared minus x squared as your surface. What I'm gonna do here is I'm gonna throw on some level curves. If I hit these two switches right here, what they'll do, everything in green is just a level curve that is above the XY plane, and then everything in red is below. So that if I turn off the surface and take on that bird's eye view, we actually have ourselves the contour map. Maybe it would make sense to zoom in just a little bit on this one to see the difference between that distance between these level curves. Well then anyway, so that's it for the first one. For the second one, let's go ahead and put that one on first. So this is kind of like a cool sine x plus sine y. You got that sinusoidal effect both parallel to xy plane and xz plane. There it is, xz plane and yz plane. There it is. I guess on the xy plane it just looks like this. But anyway, let's go ahead and turn on those level curves. So everything in green is above, everything in red is below. So if I turn that off and get that bird's eye view, you can see here this is what we're looking at for the contour map for sine x plus sine y. All right, last two. This next one is just a plane, right? Don't be fooled by the shape here. It is not a hexagon. It is a plane. It's just within the restrictions of this, kind of cubic space, right? Like cube-like, I guess. It's inside of a cube, right? This is a cube. This is a cube, right? Anyway, what we can do is we can draw those level curves. So again, everything in green above, everything in red below. So if I get that bird's eye view going on, we can see that, these all look like lines, and that should make sense. The intersection of two planes is a line. All right, and then for the last one here, we have ourselves x squared minus y, which is this, kind of looks parabolic if you look at it over this like line here. Okay, there it is. So if you kind of look, I guess parallel to this plane, it looks parabolic. But anyway, let's go ahead and turn on those level curves. And then if we turn off that surface, we can get that bird's eye view. And you get something that looks a little like this. So yeah, just like one more time, with really complicated surfaces, and you can just see here I just was slapping a keyboard and I just had this crank out. If we were to want to study this in some two-dimensional plane as like that bird's eye view, removing that z-axis, what we would do is we would just scan that plane that z is equal to k plane through, and that intersection would create this curve as it moves its way up and down. Well, I can turn that off, and I can turn off the surface as well to see all of these curves as this bird's eye view to give you an idea. Hopefully you're not like totally against this notion that this does an okay job at visualizing this, right? So that's the hope and dream, that you see the utility behind the contour map. That's it for today. Math on.